So in this video, we're going to discuss workflow and circulation. So I want to know the work done by a vector field over top of a curve. So, the blue oriented line segments of the blue vectors be the vector field and the green curve be in C. I want to see if I pop a particle on this curve, I want to know what that blue vector field is going to do to this particle. So if I put a particle, say like here, I can see that the blue vector field is actually moving in this direction. It's not moving completely parallel to the curve, but there is a parallel portion to this blue curve in that this blue in the direction of C. So what I want to do is I want to zoom in on this particular vector component with that curve. So this is that vector component. Again, if I pop a particle here, I know that that particle is going to move across that green curve. So you can kind of think of this as train tracks and this blue line segment being the wind. So if I put a particle right here stuck to this tracks, I know that that wind is actually going to move that particle along that curve. But how much is the wind going to affect that particle? Well, the wind really cares about the direction of the curve over top of this field. So what I need to do is I really want to decompose this blue vector over top of that curve. I want to know how much of this curve is going into this direction. And we do that by direction is that this is the tangent or this is the direction of that green curve at this particular particle spot. And I want to know, how far this blue curve, the decomposing its unit tangent vector of this in that particular direction. And we can do that through a dot product. So we'd have to do this, a bunch of times. There's going to be a bunch of, T sub k's here, a bunch of T sub k's all the way across this curve. So if I want to know the work done, I have to sum up all those dot products of f of k and T sub k in terms of its, multiplication with its arc length. So turn this into integration. This is going to be the integral from time A to time B of our vector field dotted with our tangent, unit tangent vector in terms of its arc length. So we define the work integral to be the integral from t equals a to t equals b of f dot t with respect to its arc length. Not very useful to us as it sits, because really what I want to do is I want it to be everything to be really in t's and with respect to our functions. So what I know is I know that the unit tangent vector is described by this. It's v over the magnitude of v, or 1 over the magnitude of v times v. So this is 1 over ds dt times dr dt, and we can see that that it would simplify to dr ds. So I can simplify this unit tangent vector to be dr ds. So this thing will simplify to the integral from a to b of f dot dr. Now still kind of close. I want everything in terms of t. So this is equivalent to the integral from a to b of f dot dr dt multiply with respect to t. So determine the work done by the field f, y minus x squared I, z minus y squared j, and x minus z squared k over the curve r of t, ti, t squared j, plus t cubed k, from the point 0, 0, 0 to the point 1, 1, 1. Now note that we want to figure out the work done. It's going to be this formula. Work is going to be the integral from, remember this is t equals a to t equals b of f dot dr dt with respect to t. So things that I'm going to need is I'm going to need to know what is f, evaluated on the curve, and I'm also going to need to know what the derivative of that curve is. So what dr dt is. So we're going to need f evaluated at c and whatever dr dt is. So first, f evaluated at that curve. Oh, we're also going to need, t equals a and also t equals b. I need to know what a and b are. So first, let's figure out the curve evaluated at c. So f, let's just say evaluated at the curve is going to be equal to, note that this is your x coordinate, this is your y coordinate, this is your z coordinate. So if I want f evaluated at c, we know that x is going to be t, y is going to be equal to t squared, and z is going to be equal to t cubed. So we're plugging those into there. So f evaluated at c is going to be equal to y being t squared. So t squared minus x squared, which is going to be t squared I, plus z, which is going to be t cubed minus y squared. So t squared squared is going to be t to the fourth, and that's going to be j, plus x, which is going to be t minus z squared. So t cubed squared is going to be minus t to the sixth, and that's going to be in our k direction. So simplifying, this is going to be 0, so it's going to be 0I. Now I need to know what dr dt is. So dr dt is going to be, the derivative of this thing with respect to t. So this is going to be 1I, plus the derivative of this is going to be 2tj, plus the derivative of this is going to be 3t squared k. So now I know f and dr dt, which means I'm going to eventually be able to find their dot product, but I also need to know what a and b are. So remember that this curve is going to go through the point 0, 0, 0 and end at the point 1, 1, 1. So I just have to figure out the t values that make that true. So it's almost as easy as just figure out your first coordinate. What t value would make this 0? So if I plug in t equals 0, well, this would be 0. 0 squared is also 0. 0 cubed is also 0. So I can see that the very first one, t is going to be equal to 0. Now, next, I needed to go through the point 1, 1, 1. So I'll just figure out this one first. So what t value is going to be 1? Well, if t is equal to 1, then this will be 1. If t is 1, then 1 squared is also 1, so that works. And 1 cubed is also 1, so this also works. So this is going to be t is equal to 1. So now we know this integral. So I'm going to do a little erasing because I'm going to need a little bit of room to work this out. So in order to fit this in this spot, what I'm going to do is I'm going to find the dot product of f and dr dt. So f dot dr dt, well, f at the curve, is going to be the dot product of, this vector function and this vector function. So you just multiply their corresponding components and then add those together. So 0 times 1 is, 0 times 1I, plus now I'm going to have to multiply the second two components. So this is going to be 2t times t cubed minus t to the fourth. That's going to be j. And then this is going to be 3t squared times t minus t to the sixth. I don't know why I have these ij's and k's in here. So the dot product is going to be the sum of those things. So this is going to be equal to 0 plus 2t to the fourth minus 2t to the fifth plus 3t cubed minus 3t to the eighth. So this will simplify to 3t squared plus 2t to the fourth minus 2t to the fifth minus 3t to the eighth. So that is going to be our dot product. So writing this up, we know it's going to be the integral from 0 to 1 of this expression. So 3t squared plus 2t to the fourth minus 2t to the fifth minus 3t to the eighth dt. So all this is just the integral of a polynomial now. So the integral of this is going to be, the antiderivative is going to be t cubed. This is going to be 2 to the fifth over 5. So 2t to the fifth over 5 minus t to the sixth all over 6. So this will be 3 now. And this is going to be 9 over 9. So t to the ninth, that'll be 3, evaluated from 0 to 1. Plugging in 1 first, 1 cubed plus 2 times 1 to the fifth over 5, 1 to the 6 over 3, subtraction, minus 1 to the ninth over 3. Minus, of course, when we plug 0 into everything, since everything has a t, that's going to all 0 out. So we get 1 plus 2/5 minus 1/3 minus another third, which in total is going to equal 11 over 15. All right, so we'll do one more example and then describe what circulation is. If arbitrary parametrizes a smooth curve C in the domain of the continuous velocity field F, the flow along the curve from A, which is the curve defined at A, to B, which is the curve defined at t equals little b, is the flow integral, which is the integral of the curve of f dot t ds. So this is called the flow integral. If you notice, this is nothing more than the work integral. If A is equal to B, then we call this flow circulation. So what we mean by that is if you're taking this curve and that curve lands at the exact same spot, instead of calling this the flow, we call it a circulation because it's ending in the same spot, it's closing the loop. So what I want to do is I want to find the circulation of this field F over this unit circle. And what the previous definition says is that I have to parameterize this circle. So I have to write this in terms of R of t. And we know that R of t is going to be, it's the same thing that we use to do polar coordinates. It's x is equal to r cosine t, and y is equal to r sine t. In this case, r is equal to 1. So this is going to be equal to the cosine of t I, that's going to be your x, plus your sine of t j, which is going to be your y coordinate, just your x and y coordinate. So again, what I have to do is they were nice enough to give us the t values, and we can see that the circulation, because as I go from 0 to 2 pi, you're going to see that it runs right back into itself. So again, what I have to do is I have to define f at r. So what is f at the curve? Remember, this is the same thing as the curve is equal to r. So f evaluated at r of t, which is really f evaluated, we wrote it this way last time, f evaluated at the curve, is going to be equal to, well, y is going to be the sine function, so minus the sine of t I. Remember, this is your x and this is your y. And then plus x, which is going to be the cosine of t, and that's going to be your j function. So plug x and y into here. I'm also going to need to know what is dr dt. Well, the derivative of this, this vector function r, is the derivative of the cosine is going to be minus the sine of t I, and the derivative of the sine is going to be cosine of t j. And last, I'm going to have to find their dot product. So what is f dot dr dt? So multiplying is negative sine of t times negative sine of t minus sine of t times minus sine of t, plus, the product of the next one, which is going to be cosine of t times cosine of t. So what we get is we get sine squared of t plus cosine squared of t, which is just 1. So that means our flow integral, or our work integral, or our circulation integral, because it's a closed flow, we'll write it as flow, but we know its circulation is the integral over the curve of f dot t ds, which ends up being the integral from a to b of f dot dr dt, and I know this dot product is just going to be 1 dt, and I know a and b were given as 0 and 2 pi. So the integral of this with respect to t is going to be t, evaluated from 0 to 2 pi. So this flow is going to be 2 pi, and the circulation is 2 pi. So the work integral, or the flow integral, and sometimes the circulation integral are all, basically work, can be written in multiple different ways. We know this is the way we define it. The integral over c of f dot t ds. It ended up being the same thing as f dot dr. So if you see something that says f dot dr, they're saying nothing more than the work integral. And this is the way we calculate it, which is done right over there. We calculate our f dot dr dt with respect to t. So f evaluated at c, the derivative of our curve, and then the dot product of those things, antiderivative with respect to t. The last thing we could write is that this dot product can be expanded. Let's say that dr dt is g prime, which was the derivative of the x coordinate, derivative of the y coordinate, derivative of the z coordinate. So you can see this just represents the dot product of these things, expanded form. So I can rewrite this as x prime is just dx dt, dy dt, dz dt. We're just writing those three things. And so that means that this will simplify to this. So if you see this integral mdx plus mdy plus pdz, you're talking nothing more than the work integral. And that's it.